to the cloud. Okay, he should be good. Okay, guys, so welcome to week 2 of our special relativity lectures. Before we start, I think we should go over logistical issues. Hopefully this video will be up for the people that couldn't make it. Let's go over some logistics first, though. So there will be a problem set this week. There was no problem set last week. After today's lecture, Gabe will be giving a special lecture on the path integral for the harmonic oscillator, which I encourage those of you that are here to stay for that, because it's a very, very useful thing to see. And frankly, if you understand that, you'll be able to understand the path integral for anything in quantum field theory. So it's like a really good thing to see and ask questions about, because when you're learning difficult physics, the only benefit to you coming here live and listening to me do it is not to listen to me do it. You can listen to me talk about this right after on YouTube. It's you have the chance to ask me questions and we can discuss this stuff. That's not something you can do on YouTube with some random video. So that's a good thing. So you should do that with Gabe. And now, so that problem set will be due next week. Now, can someone remind me when I asked for your paper topics to be due? Did I ask them to be due next Saturday? Because if I did, then I'll just make I don't know what we'll do about the problem set. But did we have paper topics due next week?
Yeah.
Okay, that's fine. Okay, so, give me a topic like you did last time. It could be about anything in quantum mechanics, not special relativity, because that wasn't what we learned. So it could be about the path integral, could be about anything you want. And again, next Saturday, Gabe will do a problem solving session, but next Saturday, I'm giving you a very brief overview of quantum field theory. And my hope is I'll spend about 45 minutes on that, not very long, and just give you the brief overview. What is QFT? Why do we need it? What are some of the basic foundations of the subject? And then I'll spend 45 minutes, and if you want to talk about your research papers or research questions or any questions, I'll do that. Usually I do it on Sunday, but I'll do it today, next week. So Gabe is doing a very special lecture after today. I don't know if I'll record it because I want you guys to get it, those of you that didn't show up. But maybe we'll record it, we'll see. Okay, so that's that. So your paper topics are due. And this is sort of the final paper is sort of like a chance for us to all hear each other talk about the subject, because I don't think we've had that experience yet. It's good to hear each other talk about physics. It's good. You guys, for those of you that will end up doing research with me, I think it's good. You should all get to know each other, for those of you that will stick around, because when it gets tough or when problems get tough, you need someone to discuss them with. You can't get through physics. You frankly can't get through life without having people to talk to about things. And God knows how many collaborators I have to get through a single problem, and how many times I get stuck on a problem. I get stuck all the time. And everyone gets stuck. Really, this is a fact. So everyone gets stuck, right? It's a question of how you respond to that. How do you respond to being stuck? And that's what makes people and breaks people. So don't get so bogged down if you get stuck. Okay, so that will be that. We'll have our final lecture next week of this term. Woohoo, right? It's been a long journey since August. And then we'll have your presentations. It depends how many people are doing it. Maybe the presentations will be 20 minutes long. Maybe they'll be 15 minutes long. I don't know yet. And maybe we'll split them in 2 weeks. Maybe we'll just have 1 week. I don't know. It depends on who's doing it. What kind of topics are you doing? How in depth? And then after you present, we'll have questions. My request is everyone who comes, and it's on record now, I won't forget, but I'll remind everyone who comes should ask at least one question to the presenter, at least one. So the presenter has 6 or 7 questions. I will be asking a lot of questions, but everyone should ask questions. It will be a good exercise. So we'll see. Okay, fine, good. And as always, if you have questions about it, let me know. Okay, anything about logistics before we begin? Okay, okay, good. Okay, so let's do a brief review of special relativity because I realized that my whole lecture from last week got messed up, which is okay because I feel like everyone was pretty much there last week who was gonna need it. So let's talk about special relativity. I'm just gonna put up the probably what, 6 or 7 basic equations that we learned. And if you have questions about those equations, do let me know because those are important. So what was the first important thing we learned? We learned about the Lorentz factor. Right, so we learned that this thing gamma equals 1 over 1 minus v squared over c squared. This was our Lorentz factor, right? This was sort of the defining quantity in special relativity because it tells us the rate at which time slows down, length contracts, all of the kinds of things that can happen in special relativity from a dynamical point of view. Okay. And as you can see now, when you're at your next dinner party, I don't know if high schoolers go to dinner parties, but if you're at your next get together or hangout, you can say, hey, I can show you how much time would slow down. And of course, this is in our special relativistic limit, right? This is when v is really close to the speed of light, when the velocity is really close to the speed of light, right? This difference is not, and you can see that in this square root in the denominator. This difference is not something you would see in daily life. Otherwise, life would be pretty damn weird. Okay, fine. What else did we learn? We learned about flat space, right? Right, so we learned about this. I love how I can just write a small little equation and it has everything I need in it. I don't even really have to explain anything now, right? Because we all know what all this means now. Hopefully, fingers crossed. So this was sort of our defining equation of a couple things in special relativity. The first is the geometry of special relativity, right? That we're in flat space. The geometry of special relativity is defined by this object here. This object here is called the metric. So the metric tells you about the space. Now, for our purposes in QFT, we're not dealing with anything fancy. We're not going to have some insane metric with weird stuff going on. We're going to be working in flat space, right? And we know that that metric has a signature, right? Minus, plus, plus, plus in our case. Sometimes they do plus, minus, minus, minus. And we know that this ds squared, this is the really important bit, this ds squared is our invariant line element between frames. What do I mean by that? This is a quantity. Doesn't matter what frame of reference you're in, observing events, each observer will measure the same value for ds squared. And that's what makes it, it's a scalar. And that's what makes it kind of a special thing, right? Because it's kind of this object that everyone's going to agree on. And you'll see in certain physical situations, it becomes very useful. So this was sort of another thing we learned. We learned about, whoa, woof, dust everywhere. We learned about 4 vectors, right? So we had this object x mu, right? We could write it as dx mu or whatever x mu. And mu ran from 0 to 4, 0 to 3. Still trips me up that we don't go 1, 2, 3, 4. We go 0, 1, 2, 3. It's very annoying, but and we know that this object is a column vector, right? It's not a matrix, it's a column vector, right? So really x mu equals x0, x1, x2, x3. And in a Cartesian basis, this is ct, x, y, z. Right, so these were sort of the mechanics we learned. And then we took the scalar product of 2, 4 vectors, right? A mu, right? We moved the indices up and down. We showed that the dot product or the inner product between 2 basis vectors gives you the Kronecker delta, right? We showed that the Kronecker delta is an identity matrix, right? We did all of these kinds of things, which I'm not going to do now. That's what last week was for. So these were sort of the basic building blocks, right? And then we built on from here, right? We showed that you could work with this object called a space-time diagram. that has time on the y-axis and all my spatial components, x sub I, on the x-axis, right? And we showed that we could have particles moving on this diagram, right? We called this line a world line. Right? And we said you have some particle, it is a function x mu now, right? Because it has 4 coordinates. It's x mu of s on this path, right? And a little infinitesimal path is called ds. Okay, so we had world lines, we had particles moving in world lines, we talked about these diagrams. Then we got to the nitty gritty. We got to maybe the most important thing of last class. And please remind me if I'm missing anything, because again, I didn't really write out any lectures for special relativity. I just figured we'd just go and I just explain everything you need. Because special relativity isn't that bad. It's kind of like the math isn't too crazy. And then we learned about something called a Lorentz transformation, right? Which took me from frame to frame, right? And we learned, first of all, more mathematically, we learned that the Lorentz transformation is a group, SO31, which you saw in your homework, right? So we learned about SO31. For those of you that don't know group theory language or who didn't have a chance to go through it in the homework, I'm going to break this down for you in a second. What is the definition of a Lorentz transformation? Purely mathematical. All a Lorentz transformation is a boost. What do I mean by boost? A boost is simply this. I have CT, I have XI, and what is a boost? A boost is just when my coordinates change and my axes shrink. So this would be CT prime, this would be XI prime, right? And we saw this last time, the hyperbolic transformation. That's a boost. And depending on where the coordinates move, this would move closer together or further apart by some angle theta, right? And we'll write out this transformation. We wrote it out last time, right? We wrote out the equations. So that's one kind of Lorentz transformation. What's another kind of Lorentz transformation you saw in your homework? You saw rotation. So in one homework, you saw two-dimensional rotation, if you guys remember, right? Where you had Rij as a 2x2 rotation matrix. In another homework, you saw Lorentz transformation as a rotation with Cauchys and cinches in the matrix, right? In both situations, boosts and rotations, what are the objects that tell you it's a Lorentz transformation? The Lorentz matrices tell you that you have a Lorentz transformation, right? And you'll have a Lorentz matrix in the x direction, the y direction, and the z direction for each transformation. And the set of those matrices make up this group, SO31. Why is it 3-1? Well, we have 4 dimensions, 3 spatial and 1 temporal. That's why 3-1. Why do I have the O? Each matrix in that group is orthogonal to one another. In other words, the determinant of each matrix is equal, but no, that's the special part. See, sometimes I have to remind myself. Orthogonality means that all of the matrices are Hermitian, right? In other words, the matrix equals its complex conjugate transpose, right? Is the Hermitian conjugate. They're equal to one another. I should probably write that. In other words, lambda equals, so lambda is my Lorentz matrix, equals lambda dagger, right? Where dagger is the complex conjugate transpose. Okay, that's a little confusing, but that's what it means to be orthogonal. And the special part means that the determinant of each matrix is equal to 1. So you should check these attributes, and you did in the homework, actually. You proved that the Lorentz matrices were a part of SO31. And you use that identity that cosh squared theta minus sin squared theta equals 1, and then you got the determinants right. Okay. Now there's another group called the Poincare group, right? And the Poincare group is sort of the grandfather of the Lorentz group, right? The Lorentz group is like one child in the Poincare group. In other words, the Lorentz group is a representation of the Poincare group, and the Poincare group includes translational symmetry. Okay. So we learned about Lorentz transformations. These were called boosts, right? right? And then we had a similar really beautiful expression, right? Dx prime mu equals lambda mu nu dx nu, right? That was our really beautiful expression. These lambda mu nu's, I can write out the one for boosts. If I get this wrong, correct me, because sometimes I forget. Lambda mu nu was, I think, it should be cosh phi or theta minus sinh phi 0 0 minus sinh phi cosh phi 0 0 0 0 0 0. Oh no, it should be a 1, right? And then 0 0 0 1. And from this equation and this equation, we obtain our Lorentz transformation, right? And I can just get it now just by looking at this apparatus. So I have d, I'm going to ignore the differentials. So what are my Lorentz transformations? Ct prime equals, did I do this wrong? Minus, then I need a plus cosh. I might have gotten this Lorentz matrix wrong, but you can recover the Lorentz transformations from this. I might have mixed up the sinh and the coshes. I don't know if someone has it handy, they can check. If not, it's okay. We'll ignore that. Okay, and we saw that, of course, these are just hyperbolic transformations on the plane for boosts. Okay, and that's why these sinh and coshes are coming up. So
you have it right. It's good.
Oh, it is right? Okay, good.
Yeah.
So then let's write out the Lorentz transformations. So then Ct prime equals cosh phi. This would be t plus, minus sinh phi x. See, that's the beauty of physics. Once I get the object, now I can do all the manipulations I need. I don't have to worry. But if I got the initial object wrong, which is obviously just, I mean, it's not pure memorization, but to derive this is going to take me some geometry and thinking. So, and then I would have x prime or dx prime equals minus sinh phi t plus cosh phi x, right? And then I had y prime equals y, and then z prime equals z, right? So this whole, the bottom line, if you can't get from here to here to here, you need to slow down and make sure you can, right? If you can, then you're good with special relativity. Okay, that's it. Now, we learned that this idea of Lorentz invariance is super important to quantum field theory. What is Lorentz invariance? Well, we know in quantum field theory, we're going to have relativistic collisions, very high speeds, very high energies. And we want to make sure that between frames, the Lorentz transformations maintain the integrity of the physics. What do I mean by that? We want to make sure if we have two different observers, primed and unprimed, whatever, that both of them are going to see the same physics, that there's a certain kind of Lorentz invariance between frames. And moreover, we want an even stronger symmetry in quantum field theory. We want to say that there's no difference in coordinates between frames. We want total Lorentz invariance. We don't want any discrepancy. And that is a really crucial way in how we construct the Lagrangians in field theory. And you're going to prove that the Lagrangians we construct are unchanged by Lorentz transformations, right? Like, for example, this is the most famous identity you all proved, that lambda transpose eta, lambda equals eta, right? So this is a beautiful example of how this metric, right, remains invariant under Lorentz transformations. You could act Lorentz transformations on it, the metric is not going to change. And that's useful. That means like we don't have to change the metric every time we do a new problem, right? Like imagine if for each observer, like I wanted to calculate something for me, for Jenna, and for Bob. Now imagine how much of a pain that would be if each time I had to change my metric. Oh my God, that would be god awful. And plus it would be very confusing. We wouldn't really even know how to change it. What are the rules to change the metric? I have no idea. Now in general relativity, you'll see that this holds for any metric, G. This holds for any metric. So it's really, I mean, we're constructing these things very, very precisely. That's the point I'm trying to get across. Okay, this was basically what we covered last time. Obviously, we did a lot more detail, as you guys know. We really derived things, and we derived gamma. We really thought about it. We looked at the postulates of SR. Any questions before we go into the dynamics of special relativity today and the principle of least action in special relativity? Okay, excellent. Okay, now let's talk about how we actually do physics in special relativity. Like, what are the ways in which we change our quantities? Oh, one thing I forgot to mention, we looked at light-like, time-like, and space-like separation between points. Do you guys remember that? If ds squared is less than 1, greater than 1, or equal to 0, that's another important thing to think about, causality and all of that kind of thing. Okay, we really covered a lot last time, which is good. So I'm going to start today by writing out a different version of the Lorentz transformation. So this is a version of the Lorentz transformation that is used a lot in special relativity. Also, you guys remember we had beta equals V over C. I showed you beta, right? And minus, okay, we did all of that. Fine, good, good, good. Okay, so here's our Lorentz transformation in a different form. I want you to see this form because it's different. Okay, so that's T prime. Should be C squared. Is it T? I always have to like remind myself. Yeah. X minus VT. Y prime equals Y. Z prime equals Z. And if I want to go backwards, I'll just write that here. It's gamma T prime plus C squared. Inverse Lorentz transformations. So this is a different form to write it in. If you start with hyperbolic transformations, which is what we did last time, and there's a way to get from there to here. I'm not going to waste our time doing it. You can look it up. It's a little trivial. And it should not be a shock to you that you see gammas everywhere. Gamma is sort of our way to get from one frame to another in a lot of respects. So these are the Lorentz transformations in a different form. Sometimes people use this form, sometimes people use the other form. Depends on the problem, depends on the situation, so you should know it. Okay, so now we want to start defining our normal quantities that we define in classical physics in special relativity. What is a velocity? Obviously, our velocity is not going to be a normal vector. It needs to be a 4 vector, right? It needs to be upgraded in a sense. So now I want to define my, oh, did anyone need that or did everyone get that? Okay, good, good. Okay. So now we want to upgrade everything. But before we do that, I want to first show you a very specific parameterization we do. So let's look at our space-time diagram. We look at X on the x-axis, the spatial components. I just put the I there to remind you. Look at CT, and we have some world line, X mu. And I told you that I parameterize this by what? By S, right? S is my parameter that it's dependent on. That's what parameterizing means, right? You have a function, you could have f of x, f of y, f of z, f of cupcake, f of bread. That's a parameter. That's deciding how your function is going to behave, right? This is just what we learn in high school. They say you have an input, you have an output, you have a function, right? So the parameter is x, y, z. What is the variable? So I parameterize this path x mu by s, okay? But now I'm going to parameterize it by something different that's going to be more useful for us. There's a very important quality of this path, and that quality is called reparameterization invariance. What do I mean by that? I mean, if I give you a brown paper bag And I say, I want you to come up with a coordinate system to describe the paper bag. All of us will come up with different coordinates on the bag, right? I might have a different way, you might have a different way. It doesn't matter what coordinates we use, the physics or the object is going to look the same, okay? In other words, it's the actual physics of the object is invariant between different parameterizations. Similarly, I can parameterize this path by any quantity I want. Doesn't matter. It's not going to change the path. And so in special relativity, we have a special quantity called tau. And tau is defined in the following way. Tau is equal to, so tau, d tau, equals dt over gamma. Okay, so what does this mean? So tau is called the proper time. And I'll tell you why it's called proper time in a second. It's a very, very important parameter in QFT and in special relativity. Okay, and we have this, this relationship that ds squared equals minus d tau squared. This is from our metric, that minus sign, and this is it's kind of a temporal quantity. What do I mean by proper time? Okay, so we've already discussed that it's really, really complicated in the special relativity with times, right? So let's say me, Jenna, Serafina, and Bob, and Mansour, we all measure different time. And who did I miss? Artem. Okay, all of us measure different times. Okay? That's confusing. And so we can have one time that everyone is going to agree on, and we're going to call it the proper time. That proper time is the time from an inertial frame of reference. It's from a frame of reference that is not moving relative to any other frame. It's like an imaginary frame of reference. That's why it's dt over gamma. It's the actual proper time. Okay? Now, this is where it gets confusing. Proper time is a scalar, just like ds. All of us will agree on it. It's like our scalar time, we could call it. That doesn't mean that me, Jenna, Serafina, Artem, Bob, and Mansour are going to disagree, are not going to disagree. We're still going to say we measure different times on our clock. So our times might all be different and jumbled up, but the proper time will be the same. So now I have, see, because here's the thing. I can't parameterize this path by t. I can't, right? I can't call this x mu of t. That literally makes no sense. What t? What t? My t, Jenna's t, Bob's t, Mansour's t. I can't say x mu of t. That's a mess. But I can say x mu of tau. I can't do that. Okay, that's why I'm being very, very precise about this. Okay, so now we have a new parameter, proper time. And this is important, right? This is super important. Why? And if I have a little d tau on the path. Why is this important? Because I want velocities. I want momentums. I want forces, right? I want my dynamical quantities. And all of you guys know from calculus, how do you get the derivative? How do you get the derivative? How do you get velocity? You differentiate position. But with respect to what? With respect to time, right? Velocity is a time derivative. So I need some notion of time, and I can't use t. I use tau, okay? So that's why we introduced this parameter. Now, a parameter, just get very comfortable with the idea of parameterizing, because you need to parameterize things by what's most convenient in your situation. In special relativity, it's really easy, right? Special relativity, I hope you find it to be a little easier than quantum mechanics, right? It's just easier. That's why it's nice to learn. So this is our situation. So now I'll define a velocity. So I define the forward velocity, u mu equals dx mu d tau, right? I can't write dt. That's why I introduced tau. And x mu is my position time 4 vector, and this is my forward velocity. Okay, beautiful. And if I integrate along the world line, I get my full scalar of proper time. So tau equals the integral of d tau from some initial time to some final time and whatever. right? This is pretty obvious. This is very similar to if I had s equals some integral ds, right? If I was parameterizing by s, and I'm integrating each little bit to get the total path. Okay. We have a normalization. For time-like four velocities, we have the following, that u dot u, if I take the scalar product between two four velocities, I get that u dot u equals eta mu nu, carries the metric, u nu equals -1, always, for time-like. For space-like, u dot u would equal 0. For for null four vectors, u dot u would equal 0. Null, sorry. For space-like, u dot u would equal 1, +1. This is just a normalization. Nothing really earth-shattering here. Okay, and of course, I can just rewrite this equation in the following way, is equal to eta mu nu dx mu d tau dx mu d tau equals -1. How does this look on my space-time diagram? Let's say I have some world line. Now it's x mu of tau. Okay, and I have a bunch of velocities, right? And at each point, I'm going to get the tangent line. I'm going to differentiate, right? So I'm drawing my best tangent lines. Hopefully, you get the idea, right? And these are all u mu's. Okay, so that's the idea. If you have a du mu, or it's just a derivative at each point on the path, and you just have a bunch of tangent lines. That's it. I mean, it's just really, really geometric and simple. Now let's look at the dynamics. If I have no forces, then what's going to happen? My object is just going to keep moving at constant velocity, right? There's going to be no accelerations. There's no forces. It's just going to keep moving along, right? Newton's laws of motion, Newton's third law of motion. You need second law of motion. It's going to keep moving unless acted on by an outside force. How do I represent that? I write that my equation of motion, du mu d tau equals 0, right? Because du mu d tau is the acceleration, right? It's the derivative of the four velocity. And that's just going to be 0 because there's no acceleration in the absence of forces. This is my equation of motion. Very, very simple. Okay, now I can write F equals ma, right? M du mu d tau equals F mu. That's F equals ma. Okay. So we're just promoting everything to four vectors now. That's all. Very, very intuitive. And of course, A mu equals du mu d tau. Therefore, F mu equals m A mu. Okay. Those of you who are learning Calc 1, you should be very happy because this is literally what you learn in the first few weeks. They teach you some physics, actually, in Calc 1, which is good. Okay, but now we know that u mu is going to have four components, right? u0, u1, u2, u3. So now let's define them. Any questions about what I did here with everything? Okay, very good. And I can erase? Okay, good. Thank you, Jenna. You're my clock if I can erase or not. Okay, nothing complicated so far. Like I said, special relativity is not, oh, we're going to derive E equals mc squared. We're getting there. We're getting there. It's not as big of a deal as you think. You're going to be kind of underwhelmed. I was when I learned it. Okay, so we define u0 as dx0 d tau, right? We know that d tau is equal to dt over gamma, right? That's what we defined it as. And we know that dx0 is dt, right? Or dct. By the way, I keep bringing up C and taking it out because a lot of times we just set C equal to 1. Did I mention that last time? Yes? Okay. This is super important. We usually just set C equal to 1. The only reason I'm keeping it in special relativity is because E equals mc squared. So I'm keeping the C's just to make it, work. But in QFT, we're never going to see a C again. So don't worry. We just get rid of it. Or an H bar. We just get rid of it. So this is equal to what? dt, okay, over 1 over gamma. Oh no, this should be, dt. dt. Right? Because that's dt over gamma, dx0 is dt, and this is just equal to gamma. Okay? See, this is why I want to bring up the factor of C here. I'll show you why. It's not, right? I could just write it like that if I set C equal to 1, right? dct. So now u mu equals gamma C ux uy uz. I should really write this as u lower mu, right? Because I wrote this as a row vector. Remember? Lower index is a row, upper index is a column. So just to be more precise. And this is my four velocity. Oh, shoot. We'll write this as v. Vx, vy, vz, just to be more clear. Okay, so this is my four velocity. Very simple. I just have that factor of gamma. It's nothing really complicated. Okay, let's look at momentums, which are super important in special relativity and in QFT, because momentum conservation is super important. So classically, we have P equals mv. Obviously, we know this is not going to be good. What is V? V is not a defined quantity in special relativity or in relativistic situations. So this becomes P mu equals m u mu equals m dx mu d tau, right? So that's my momentum, for momentum. Once again, we need to define these objects, right? We define P0 as mc over 1 minus v squared over c squared, square root, i.e. mc gamma. Yeah. That's the 0th component of the four momentum. And we define the spatial components of the four momentum, p sub I, as mv over 1 minus v squared over c squared equals mv gamma. You should notice something very interesting here. So the four momentum is a very important quantity. It's probably the most important quantity. This is what we define is going to come to mean an energy. And you'll see in a second what I mean by that. Okay, we define the relativistic energy as this, and you'll see why. I'll derive why. But we define the relativistic energy as mc squared over 1 minus v squared over c squared. Okay, equals mc squared gamma. Okay, that's the relativistic energy. And so therefore, p mu as a full four vector goes E over C. Again, usually the C is just 1. All of these factors of C, we just get rid of usually. So don't be so bogged down by that. Px, Py, Pz. Once again, I should really have the mu lower, right? And this is our full momentum four vector. And the full name for this is energy momentum four vector. Really important, right? Why do we call it that? Because the 0th component is the energy. That's just how it works in this construction, which is super useful. So, in quantum field theory, we're going to write a lot of these p mu's out, right? Because we want to know the momentas of different particles as they collide. That's important. And always in the 0th component, we're going to put an energy. So that shouldn't look mysterious to you when we do it, because that's how we've constructed this here, right? And this is super simple. It's not very complicated. We're just defining things. Gammas are just the really gamma's really the only difference, right? Otherwise, it's really just classical. All right, and if C equals 1 and you work out this dot product with the gammas and everything, you get that P mu equals m squared. Okay, that's another important quantity, the dot product between two momentum 4 vectors. Now, what's super interesting is in quantum field theory, sometimes P mu does not equal m squared. So when P mu equals m squared, we say in quantum field theory jargon, just so you start learning it, we say we are on the mass shell. You'll see why when we do QFT. And in when we do Feynman diagrams, P mu does not equal m squared, and we go off shell. Not really so important now. Okay, we go off shell. So if you ever hear a particle physicist say, "Oh, you can't go off shell in that method or on shell," this is really the defining feature of that, and it has real consequences. It's not just trivial. Anything confusing here? Speak now and forever hold your peace, because now we're going to derive equals mc squared. So, okay, very good. Man, special relativity is nice. It's not so complicated. We're not sweating as we do derivation. Oh my God. Okay. What a contrast from QFT, where we're going to be sweating every class. We're going to be sweating. It's going to be so bogged down. Okay, so again, we have P mu. I'm going to drop the C. Is E, X, Y, Z, our energy momentum 4 vector. And we define the relativistic energy as E is defined as mc squared over 1 minus v squared over c squared, the square root, i.e. mc squared gamma. Okay, and now this is the full relativistic energy. I have made no approximation here on the energy, right? It's dependent on the speed. It's dependent on only the speed of the object, okay? And the mass, which makes sense because that's how energies work. Now, I can approximate this energy. right? In the limit, if V is way smaller than C, then what is my relativistic energy? What is the relativistic correction if the speed of the object is much slower than the speed of light? Okay, and that's where E equals mc squared comes from. It's the lowest order relativistic correction to the energy. Okay, so it's a correction, right? Because it's like Newton's laws are almost right. They're like 99% right, but you need relativistic corrections. And if you're going much slower than the speed of light, you don't have to worry about second order corrections and third order corrections and so on, right? You only have to worry about lowest order corrections if you're going really slow. The fact that it's such a beautiful consequence and that it's so profound is just luck. But really, from a mathematical point of view, it's nothing profound. It's just the lowest order relativistic correction to the energy. But the fact that it turned out to be E equals mc squared, and there's this connection between energy and mass, is like a cherry on top. That was not expected. So let's do it. So I can write this as E equals mc squared 1 over 1 minus v squared over c squared, square root. And now I want to expand this thing in a Taylor series. Okay, because that's I can expand it and approximate if V is much less than C. So I can write this as E, and we actually did this in the special relativity class I taught at the library. So hey, we did this Taylor series thing. So what do I get? I get mc squared. I'm not going to expand that. I get a 1 plus 1/2 v squared over c squared plus 3/8. Wait a second. Yeah, 3/8. V to the 4th, c to the 4th. That's my Taylor series. And of course, I could keep going and going, right? I just stopped at this term, right? This is really an infinite series. And so this really equals, so E equals mc squared plus 1/2 mv squared plus 3/8 mv to the 4th c squared, right? Okay. Now I have my approximation to the energy, and you guys should start going, woohoo, I see the magic equation right there. So this is the first order approximation, right? So in the limit, where v is much less than c, and this correction still stands if v is close to c, right? It's just that you need these higher order terms as well. You get that E naught equals m naught c squared. And we define this as the rest energy for good reason, because we're moving slow. Right? In a relativistic context, we're moving really slow for this to be the energy. So that's why all the mugs are wrong. It's not just E equals mc squared, it's E naught equals m naught c squared, because it's really a rest energy. It's not like the actual energy. It's a correction, a really, really crude correction. And this m naught we usually call the rest mass. Okay, so now you can tell all your friends, that's just a Taylor series of gamma. That's all. It's not really a big deal. It's not as big of a deal as people make it out to be, but the consequence is really profound. Because now we're saying there's this equivalence between energy and mass. This is a really, I mean, you need to like step back and like, you need to step back and think for a second. Because this is a really profound consequence. I'm telling you that if even an object at rest, as long as it has mass, it has energy. So I was in high school. I'll tell you the story now. I was in high school. We didn't have a great physics curriculum. I was teaching myself special relativity. I was probably a sophomore or freshman. And I would go and bother the physics teacher every day after class for every year until I took her class. So I got to know her very, very well. And she actually came to some of these lectures at the beginning to give me tips, but we had so many students and you guys didn't meet her, maybe later. And I did the calculation. I said, oh, Miss DeLise, there's this beautiful E equals mc squared. She says, of course, everyone knows that. But I says, it's pretty profound. It's more profound than when you first look at it. Because I did this calculation where I said, what if I had a kilogram of potatoes? Bob probably remembers this because I tell this story every time I teach special relativity. I said, I did the calculation to see how much energy is inherently inside 1 kilogram of potatoes. Okay, because that 1 kilogram has mass. Okay, so how much energy is in that 1 kilogram of potatoes? It's more you can't just use this. You have to use some other techniques. But I figured out that there was enough energy in 1 kilogram of potatoes to power all of Manhattan for 1 year. Okay, so this sounds absolutely insane, but that's true. That's a consequence that comes from this. Now, we don't know how to get that energy. You'd probably become very rich if you could harness it. But this equality between energy and mass is a very, very consequential one. Not just in physics, but in quantum field theory, because, well, quantum field theory is physics. But in quantum field theory, this is going to become very, very crucial. Because what am I saying here? I'm saying if you increase the mass, your energy must go up. That's a consequence. And if your energy goes up, strange things happen, as we'll see in the conceptual discussion of Q of T. You get new particles being produced. There's too much energy. New particles must be produced. And as we'll see, quantum mechanics, non-relativistic quantum mechanics, we've never looked at multi-particles, have we? We've always dealt with a single state. We've always dealt with a single state, and that's a problem. We need multi-particle states. Non-relativistic quantum mechanics says, no, I can't tell you how to look at two wave functions. I can only tell you how one wave function will evolve from Ti to Tf, right? I can only tell you this. Some psi f e to the I ht psi I, right? That's what I can tell you. I cannot tell you really about multi-particles. And of course, this is the path integral, right? This is what the path integral is telling us. Okay, any questions? Do you feel enlightened that you've derived this quantity? Okay, good. It's not that bad, honestly. It's kind of fun to see. Another quantity we define in special relativity, the kinetic energy is equal to gamma. Oh, sorry. Is equal to mc squared. Gamma minus 1, right? And this is just equal to 1/2 mv squared plus 3/8 m v to the 4th over c squared. Okay, so it's just this bit. Oh, we got another applause. Good. Okay, so that's our relativistic corrections to the kinetic energy. Okay, pretty straightforward, I hope. Okay, wonderful. Very good. Again, in classical mechanics, we cannot have a massless particle. Doesn't exist, right? In special relativity, you can have a massless particle. Okay, that's another consequence of all of this. Then you could say, well, how do we tell the difference between two massless particles or two photons? We use the frequency. Remember, in quantum mechanics, E equals h nu, right? Or in waves. You must have learned this in physics 1 or whatever. E equals h nu. And nu is the frequency. And so each photon will actually have a different frequency, believe it or not, and a different energy. Pretty awesome. So actually you have red photons and purple photons, but they're all massless. Kind of interesting. Okay. So I just want to mention two quick things about special relativistic collisions, and then we'll move on and spend the last 20 minutes on principle of least action in special relativity, which is not something a lot of people cover. I want to show it to you guys because I like it. I think it's a cool thing. Okay, so we have two things. You have three kinds of collisions, right? In general, you have sticky collisions, elastic collisions, I guess, inelastic collisions. I don't even know the names. Whatever. There's three kinds of collisions. One where the two objects come together and stick together and become one object. One where they collide off each other, right? That's kind of it. I mean, I don't know all the. I forget the terms people use. I don't really care. You always have momentum conservation. So let's say you had A and B colliding and C and D moving off, you would always have momentum conservation. Right? That the ingoing momentum equals the outgoing momentum, right? I would hope so. That's just a great conservation law. You always have total energy conservation. Okay, you always have total energy conservation. Kinetic energy might not be conserved, right? As you know from classical physics. So that's kind of the big thing. I mean, I don't really want to go too much into this. The last thing I'll say is in QFT, mass is not always conserved. So you have some, you might have a collision where you have a pion, pi 0, and you see this collision where the pi 0 goes to 2 photons, decays into 2 photons. A pion is really like 135 MeV in terms of mass. A photon is massless. So somehow we had a loss of mass, which means we had a loss of energy. But I just told you total energy must be conserved. So something has to give here. You might have a difference in kinetic energy or something. So this is interesting. We'll talk about it when we get to Q of t. I'm not going to go too much into collisions. We're going to spend like, you're going to get nauseous thinking about collisions. So I think we'll move on. Just know that there's conservation laws. And this is a really stupid way. I mean, this is like a really easy way to write it. The ingoing momentum A plus B equals the outgoing momentum C plus D. That's it. Okay. Okay, let's move on to the special relativistic action. Same ideas, right? I have an action, I have a path, I want to minimize the action. Only difference is the math is going to be kind of annoying. So I'm going to skip a lot of steps. It's okay. You just need to kind of get the flavor. I don't expect you to be able to do all of this. The action I showed you last time was easier. And in fact, some of the Q of t actions will be easier too, actually. The reason this action is harder than the Q of t actions, believe it or not, some of them, is because it's not Lorentz invariant. It's not constructed in that beautiful way I just said that we're going to construct Lagrangians to minimize. And so we need to be a little careful. That's okay. Okay, so non-relativistically, my action S and R is going to be an integral of my Lagrangian, right? That's what the action is, right? From a few weeks ago. And I will just have 1/2 m v squared of t, right? Just some kinetic energy for a free particle, right? No potential energy. It's just kind of moving along at a constant speed. I have the relationship that v squared equals v dot v, right? And I know that v equals dx dt. Okay, so this is like my non-relativistic action for a free particle. Super, super trivial. There's really no reason to do this. It's like an overkill for a regular free particle. And if you minimize this action, you're going to get what? You're going to get an equation of motion, right? That's how we derive Euler-Lagrange, right? And if you do this process, you get that the equation of motion is equal to dv dt equals 0. Exactly what you would expect, right? This is what you would expect, right? There's no acceleration, and it's moving at a constant speed. Okay, so this is non-relativistic. We're done. That's it. I'm not going to do the whole process for this. It's useless. Okay, we know in SR that ds squared equals minus dt squared plus dx squared plus dy squared plus dz squared. Okay, and I'm going to have some path. Eventually, we'll parameterize it by tau, but we can call this some path P. Okay, and the special relativistic action becomes MC integral over the path ds. You'll see why the MCs come up. Again, a lot of this stuff is just from experience. We know how to set up our actions. Okay, we have a special relativistic. I think I showed this when we did the lecture on least action, right? I showed this action. Okay, now we're going to pick one observer. Again, I'm making Never mind, it's okay. And for that one observer, they're going to have ds is not just going to equal ds on the path. It's going to be equal to, let's just say I'm reparameterizing by t. I could have an s here, but I have t, but I'm going to have my factor of gamma, right? Because now we have a different observer. Really, I should have a factor of c here. You'll see why. And my special relativistic action now for this new observer becomes s mc squared from some ti to tf, right? Now I've parameterized by time, right? That's what I'm doing here, right? dt 1 minus v squared over c squared, or gamma, right? So this is just mc squared ti to tf dt gamma. Okay, so, oh no, this is not gamma. No, this is not gamma. Sorry, or really, I could do it like this. Yeah. This okay? It's the same thing as that. Right, because this is gamma's 1 over 1 minus v squared over c squared. So if you have dt over 1 over this, that's just really multiplying it by that. Okay. Okay. Okay, so now I have a action, right? And I've chose a specific observer. I don't have a tau here, folks. I have a t. That's why I have this gamma. If I had a tau, I wouldn't need it. Make sense? Okay. I need to correct. Please ask questions if something's confusing. Okay, so now by definition of the action, this is my Lagrangian, right? Because what is the action? Again, the action is the integral of the Lagrangian, right? And so my Lagrangian for special relativity is mc squared 1 minus v squared over c squared. That's my Lagrangian. I'm going to define a few quantities for you, okay? So first, let me Taylor series expand my Lagrangian. Okay, I just Taylor series expanded that. I expanded the radical. This thing. And I defined this object, this is just a definition, called the canonical momentum of special relativity, and in general. So the canonical, oh no, the conjugate momentum, that's what they call it, or what we call it. I say they, but then I'm one of them, so I should say we. The conjugate momentum, and this is the definition of this, you should know this, because we use this in Q of t, is defined as del L, del V. This is sort of a side thing. And actually, when you do this calculation, which you should do, you find that you get mv over 1 minus v squared over c squared, which is just mv gamma. Which is just the relativistic momentum, right? The spatial components, which is good, which is what we want. This is like the Euler-Lagrange kind of thing, right? Turn the crank. We have a Lagrangian, we get the right quantity. And you should do this derivative and make sure you get this. Are we all good? Okay, I'm not going to do the derivative, it's messy. Okay, now we have this object called the Hamiltonian. And actually in Hamiltonian mechanics, the Hamiltonian must be the total energy. We know that, right? But we have Lagrangian mechanics and then we have Hamiltonian mechanics. And in classical mechanics, the Hamiltonian is defined as P dot V minus the Lagrangian. That's how we define the Hamiltonian in classical mechanics. And turns out when you do this operation with these objects, you get that the Hamiltonian equals mc squared over 1 minus v squared over c squared, which is just our energy, which is what you want from a Hamiltonian. Take my word for it. I'm not going to compute all of it. It's annoying. Okay, so anyways, like the point of doing this is just to say, okay, this Lagrangian that we've created from an action works. It works. It gives me the right relativistic energy and momentum. And if you're suspicious about that, do the calculation yourself, as every professor says in history. Okay, any questions about our setup of the problem now? Okay, and this is why we spent so much time learning about the principle of least action, right? Because now we know the procedure, we know the mechanics. We have to integrate by parts, we have to cancel one term, we have boundary conditions, the whole 9 yards. So let's do it. Okay. Okay, let's do it. So now I have some path. I have some world line. This is some x mu of tau. And in string theory, you actually get 2 dimensions, tau and sigma. We're not doing string theory, so it's okay. Again, my path is reparameterization invariant. In other words, x mu I equals what? It just equals x mu tau I, right? And x mu f equals x mu tau f. Right? Reparameterization. Invariant. Okay, I can write out ds squared. So we know that ds squared equals eta mu nu dx mu dx nu. But now I've reparameterized my path by tau. So now it's not just dx mu dx nu, it's dx mu over d tau. It's a derivative along each point parameterized by tau. Does that make sense? I've reparameterized. So now my ds squared becomes eta mu nu dx mu d tau dx mu d tau. Cool. This is where your basic calculus comes really in handy, just to think about what we're doing with the space. Oh, I need d tau here. Okay, now what is my action? My action is equal to mc squared ds. I have ds squared, right? So now I have to take the square root of this thing, and then I have my action. Integral from, do I want to do tau? Yeah, we'll do tau I to tau f of theta mu nu dx mu d tau dx mu d tau integral over tau square root, right? Because it's ds, not ds squared. Does this all make sense, how I got this action? And actually in general relativity, when you want to derive the geodesic, which is the equation of motion, because that's what we're going to get, in general relativity, you do the same thing. And now our Lagrangian is really this thing, right? So now I can just redefine the Lagrangian as eta mu nu dx mu d tau dx mu d tau square root. That's Lagrangian. Not a big deal. It's just a name. In fact, I'll erase it because it really is just a name. It's not so important. Any questions? Okay. So now what do we have to do? We have to vary the action, right? We have to perturb the action to some arbitrary path. And yeah, we have to do that whole process. That process is hard. So don't be so down on yourself if you get a little confused here, because I'm going to skip some steps. It's not a big deal. Frankly, in QFT, the process is a little easier for most things. So don't get so confused. So now I'm going to perturb my action. So delta S equals mc squared integral tau I to tau f delta ds. This is ds parameterized by tau. What is delta? So remember, I perturbed, and when we did the principle of least action, I perturbed the paths by alpha, right? I added some alpha rho to the path, and I perturbed the wrong path. So this is just my perturbation, delta, just pushing the action or the path to some wrong path, right, off this path. That all makes sense? Okay, so it's a mouthful. Okay, so if you do all of this out, you get that delta ds is this. And there's many steps. To be frank with you, it's not so important. You get that delta ds is equal to eta mu nu. As long as you know the conceptual idea of what we're doing. D delta x mu ds. Dx mu ds. That's your delta s. Delta ds, sorry, ds. And so you get that delta s is equal to mc squared integral from tau I to tau f eta mu nu d delta x mu ds dx mu ds. Yes, this should be a mu. And I'm getting sloppy. I should really have s's here on these boundaries, not taus. As you can see, I've gone back and forth between s and tau, like kind of seamlessly here. That's because I have reparameterization invariance. If I didn't, I'd be in trouble, right? Because now I'm changing everything, and you can't do that. But I can because I've just said this is an arbitrary parameterization. Okay, I mean, this step is going to be a little confusing. Okay, now we have to integrate by parts. Let me just rewrite the action here. Okay, now I have to integrate by parts, right? That object I wrote. And you're going to get some term. You're going to get a minus sign minus some integral, right? And that first term is going to be evaluated at the boundary conditions, right? From last time. So I actually did the integral on paper, so I'll just copy what I wrote because it's, like I said, it took me a while to do it. So I'm not going to go through the whole integral. So when I did it, what did I get when I wrote this integral? I wrote that delta s is equal to mc squared integral si sf ds total derivative, eta mu nu, delta x mu, x mu, yes, minus integral SISF, yes, delta x mu, MC, eta mu nu, d2x mu, yes. Okay. Don't worry about the whole integral. Yeah, it's complicated. In QFT, I'll take you through each step of these, obviously. But here, I just want to show you what we get. Okay, as always, in these things, these are evaluated. This is going to be evaluated at the boundary terms. So what is our perturbation? So remember in our original problem, we had a rho. Do you guys remember we had rho? And rho was our function that was taking it off the wrong path. Here, that's delta x mu. See, because delta x mu is what? It's x mu, that's my function. Delta x mu is pushing that function a little bit off, right? So that's the analog to rho. So delta x mu would be like something like this. Right? Just like rho. It's just pushing it off. So that should be familiar. Of course, this first term drops because my endpoints are both at the same position, just like last time. And so we get that delta S equals minus the integral from SI to SF ds delta x mu MC eta mu nu d2x mu ds squared equals 0. Now delta x mu can be anything, right? Just like rho. Delta x mu can be any perturbation. Therefore, this whole bit must be 0. Right? That's just from our perturbation. M is a constant. C is a constant. Eta mu nu is a constant. We can get rid of those things, just constants. And we get our final equation of motion. And I'm going to change the index. d2x mu ds squared equals 0, which is just what we would expect. That the acceleration for a free particle along the world line is 0 with no outside forces. Okay, very straightforward. Not straightforward in the mechanics, but straightforward in the result, and very similar to what we did a few weeks ago, classically. I hope. And I'd be happy to go over all these steps tomorrow morning if you want. I hope not. We can talk about other stuff. I don't feel. Any conceptual questions, though? I just think this is a useful thing to see because it shows you how any problem in physics, you can get an equation of motion. Now, what if I wanted to add an outside force? I would change my action, right? I would change my action. Okay. Okay, the last thing I want to show you is, and this is the relativistic particle, right? This is a relativistic particle. It's not a classical particle, right? Because now we have x mu of tau, right? We have 4 vectors, we have the metric coming in. Now I want to show you what the action would look like for a relativistic particle with an electric charge. And the reason I'm going to show you this, we're not going to get an equation of motion. I just want to show you the action because it has some important things in it. So for an electric charge, we have S equals mc squared. Integral along the path ds plus the integral, plus q over c along the path, some object a mu of x dx mu. Okay. I'm sure, so this is a relativistic particle with an electric field. This is so my point is, first of all, the first thing you should think about, we can construct actions for literally anything. Okay, I just constructed another action. Okay. But now let's think about this now. And there's a few things I want you to notice before Gabe comes in. Just a few. Yeah, I have 5 minutes. Perfect. Sorry, I didn't give you guys a break today. It's not easy to do all of special relativity in 3 hours, but we did it. So pat yourself on the back. Yes. We're like going rapid fire through all of physics. We've done everything. Okay. First of all, you see this first bit is literally your special relativistic action for a free relativistic particle. And then you get this second bit. Okay, so obviously in your head, you're going, this is what makes it electrically charged, right? Obviously, whatever's going on here. And yeah, you have some notions. You have Q. Q is a charge. But the main object I want you, and you have a path, right? But the main thing I want you to pay attention to is this thing called a mu of x. Okay. In electricity and magnetism, first of all, a mu is going to be what? A mu is going to be a vector, right? It's going to be a 4 vector. It's just another 4 vector. And in E&M, this is a 4 vector that tells you about the electric field or the force of the field. Okay? But what's really special about this object, a mu of x, is it's an object called a gauge field. Okay? So I'll just write that here. And these are going to be super important in the standard model or particle physics or QFT. And we'll see that a gauge field is a very special object because first of all, it contains, first of all, just as a simple note, it contains information about the physics. That should be obvious to you. But on a more deeper level, a gauge field has a very particular kind of symmetry. Okay? A gauge field is an object, a 4 vector, such that if I acted on this system, on these objects, it leaves it invariant. So basically what I'm saying is it's very abstract, guys. Don't worry too much about it. We're going to literally, the standard model is literally, all of it is called a gauge theory. Everything is gauge theory. So we're going to learn this really, really intimately. But what I'm saying is in E&M, you have gauge fields. It's not just a standard model thing. And the reason is that they maintain a certain level of symmetry in your action and in your Lagrangian. They leave things invariant, okay? And they help you solve things. That's all you should know. We'll talk about it a lot in depth. These become very, very important. Okay, folks. Any last questions about special relativity in general, other than if you guys want to come tomorrow? Anything at all? Who invented special relativity? Maybe that's something people are wondering.
This is kind of random, but is like the Doppler effect special relativity? What is that?
Yeah. So the Doppler effect is not special relativity. Why? Or it's not an effect that has to do with special relativistic effects. Why? Because you could experience the Doppler effect right now. Right? So what is the Doppler effect? All the Doppler effect is Okay, I'm standing here on a sidewalk and I'm in the middle of a block, right? And there's an ambulance coming. When it's really far away, the wavelength of the sound is going to be longer. Therefore, the sound is going to be quieter. And as it comes closer and closer, the wavelengths are going to shorten. Therefore, it's going to get louder. And it's going to get louder as it passes me. And then again, as it moves away from me, it's going to get quieter. All right, so that's just a classical thing. So it's going to go, and then you hear it echoing off.
Yeah.
So that's not a special relativistic effect. And actually, intuitively, you could just think about that because you could experience it right now. Does that make sense, or?
Yeah.
Okay. Okay, Gabe, we are so ready for the harmonic oscillator. I can't wait. I can't wait to see all the torture you're going to put everyone through.
It'll be fine. But yeah, it's going to be. Is exciting the right word? I don't know.
Gabe, we just talked about everyone's favorite object in E&M, a mu, the gauge field.
Mm-hmm.
So please, would you like to tell everyone what's so special about this gauge field, a mu? Now, I didn't really say anything about it, so maybe you want to give a 1-sentence or 2-sentence description of it.
Well, the thing that I find interesting about it is that, especially when you're trying to like write Maxwell's equations in some covariant form, is that you can condense these like 4 already nice equations into just one object.
One dot product, right?
Yeah.
Yeah,
So,
it's pretty amazing.
Yeah.
Yeah. And we'll see this. I mean, in QFT, guys, we're going to look at this idea of a current. Gabe, I don't know if you're familiar with Noether's theorem.
Yeah.
Yeah, so conserved currents, right? Or conserved symmetries.
Mm-hmm.
And these ideas are going to be really important. So in E&M, you probably saw J mu, right? The current.
Yeah.
Yeah, so then, D mu, J mu is equal to 0 or something like that. Or my point is, in E&M, you choose gauges a lot, right? I don't know if Al Mueller went into that. Did he go into like Lorentz gauge or choosing a gauge?
Yeah, he did.
Okay, obviously, because it's Al Mueller. So it's so funny, right? Because in a usual undergrad E&M class, guys, you wouldn't learn any of that. But the guy who taught undergraduate E&M is a theorist, so he went all out. Correct me if I'm wrong, Gabe. So
no, he did. Did I tell you how we used for like half of the course we used Jackson?
Right?
Yeah.
Yeah. Okay. Yeah. Sounds good. So you know what A mu is, J mu. You wouldn't learn that in normal E&M. Okay. Wonderful. Okay. Great. So Gabe, take over. I will be here. I will probably have my camera off for some of it, but I'm very excited to listen. And guys, I think, and Gabe, correct me if I'm wrong, I said this at the beginning, if you can learn the path integral for the harmonic oscillator, you're kind of good. You can do it for any system because it's a really good example.
Yeah, and I hope I'll probably get to talk a little bit about how to do this generally, so people just.
Oh yeah, that would be very helpful. Yeah. Okay, folks. So that's special relativity. Next week we'll do the final lecture of the term, the conceptual basis of QFT, which is going to be broad brushstrokes. I'm literally going to take you through the whole standard model. Thank you, Serafina. And your presentation topics are due next week. Gabe will send out the quiz grades for those of you that did it. And I really encourage you to do the final presentation, even if you're a little unclear. It's a good practice. And if you want to do research, you need to learn how to fail and be wrong. Very, very important. I think 90% of research is being stuck. Maybe it gets better as you get better at physics, but I don't think it gets a lot better than 90%. It might go down to 80, but it doesn't get a lot better than the 90. The 90 is kind of like a good number. Okay, Gabe, take it away.
All right, cool. Let's do it.
I'll make you the host.
All right, thank you.
Let me just stop